Now, let's continue our discussion of the scheduling criteria. Okay. The next one is response time. Response time is different from turnaround time, but it's also quite related. So, remember, turnaround time is the end-to-end time across a process entire life cycle, right? Starting from when a process is created to when the process is terminated. Well, response time consists of the time that it takes to service a request. Okay. So imagine you have, for example, you have a process that's a long-running process. Okay, it keeps processing requests. Okay, and then for such a process, turnaround time is not so meaningful because the process is running all the time. But what is more meaningful is how much time each request takes to get a response. Okay, so response time measures the amount of time it takes from when a request was submitted to the process that the first response is produced. Okay. So it is meaningful for interactive processes, for example. Interactive process which keeps taking requests and produce responses for the requests. Okay. So the response time then for such a process, response time for each individual request is more important than the total turnaround time of the whole life cycle of the process. Okay, so these are different stage metrics. Okay. And then the objective of scheduling algorithm can be maximizing CPU utilization, maximizing the throughput. We talk about the difference between CPU utilization and throughput. Both are looking at the overall performance of the system. The objective can be also minimizing the turnaround time of a process, or minimizing only the waiting time. Okay. So not including the time that the process spent on the processor, but only time that the process spent in the ready queue, waiting for to be scheduled. Or the object can be minimizing the response time. Okay, we just talk about it. This is something that would be meaningful for interactive process. So, but in most cases, we want to optimize the average measure. Okay, sometimes we want to optimize the minimum or maximum values. Sometimes we want to optimize the variance. We want to minimize the variance. Okay, for example, we want to minimize the variance of the waiting time of all processes. That would be a meaningful optimization objective. Okay, but in most cases, we want to optimize the average measure. For example, we want to optimize the average waiting time. Right? If you have a bunch of processes, right, every process will spend a certain amount of time waiting in the ready queue, and we want to minimize the average waiting time, okay, or we want to minimize the average turnaround time, okay. But that's the typical case. Sometimes we want to optimize the maximum waiting time. Right? We want to minimize the maximum waiting time. That would be also possible, okay, but just not as typical as optimizing the average measure, okay. So, or it can be sometimes we want to optimize the variance. We want to minimize the variance of the waiting time of all the processes. We want to every process to wait about the same amount of time in the ready queue. Right? That would be optimizing the variance. Okay, because those are different possibilities. Okay, but in this lecture, in this chapter, we're gonna focus on optimizing the average measure. Okay? Where the measure can be any one of this list of scheduling criteria. Okay, so with this introduction of the possible scheduling criteria, so now let's look at some real scheduling algorithms. Okay. And of course, we will be looking at the basic scheduling algorithms. At the end of this chapter, we will look at a real example of how an advanced CPU scheduling algorithm is designed and implemented for modern state-of-the-art operating systems, okay, operating system Linux. But we'll start with the basic ones. Okay, the basic ones are still important because even though the sophisticated ones, the really advanced ones, they're still built on top of this basic concepts, okay, that are used by this the basic principles, basic designs used by this basic scheduling algorithms. Okay, so the first one we'll be looking at is a first come, first served scheduling, or FCFS in short. So this is a simple algorithm, as the name suggests. Okay, the way that the CPU scheduler schedules the processes is first come, first served. The process that requires the CPU first is allocated the CPU first. So you can imagine we can easily implement this algorithm, this scheduling algorithm, right, using a FIFO queue, right? So if we implement the ready queue, where we place all the processes that are ready to run as a FIFO queue, the first process that gets inserted into the ready queue, right, will be the first one to get out of the ready queue, the first one that will be scheduled, right? So you can just implement it by implementing the ready queue as a FIFO queue. So it's just this algorithm is really simple to implement, but there's a problem. Since it's so simple, there's a problem with associated with it, and that is the average waiting time is often quite long. If we use first come first serve scheduling, the average waiting time, considering all the processes, is often quite long. Okay. So let's look at some examples. Let me check the recording is still going on. Okay, good. So let's look at some examples. Okay, so in the rest of this chapter, we will be using this so-called Gantt chart, okay, to illustrate the schedule of the processes. Okay, if you know what what Gantt chart is, right? Even if you don't know, we're gonna look at some examples, and then you can know how it works. Okay. So we consider now here we consider three processes, P1, P2, and P3. Okay, each one of them has a different CPU burst time. Okay, so we're talking about the CPU burst time here. Okay, so look at this. Take a moment to look at this example. .400 seconds. So we have been, that's roughly 7 minutes. Okay, we are 7 minutes into the lecture. Let me set a timer. Okay. All right. So let's look at this example. Okay, we have three processes. Each process has different CPU burst duration. And the unit of the time is not important here, so we just consider it's unit time, right? It can be millisecond or second, okay? It's probably more likely millisecond, okay? But that doesn't really matter, okay? We just consider it's a unit time. So P1, it has a CPU burst for 24 units of time. P2 has 3 units of time, and P3 has 3 units of time. And these are the CPU burst durations, okay? And we only consider one duration, one CPU burst, okay? We are scheduling according to the next CPU burst that we know about these processes. Okay, so now suppose the process arrive in this order: P1, P2, P3. That's the order they arrive. Okay, they all come at about the same time, but P1 is slightly before P2, P2 is slightly before P3, and then when we schedule them according to first come first serve, then we have to schedule P1 first, and P2 next, and P3 last. Okay, as simple as that, and then we can draw this Gantt chart like this, right? So we schedule P1 first. P1 has a CPU duration, CPU burst for 24, right? So it will start to run the process from time 0, and it will finish by 24. Okay, takes 24 units of time. As simple as that. And the next we schedule P2. Right? P2 has a CPU burst for 3. Okay, so it will finish by 27. And next we look at P3. We schedule P3. P3 has a CPU burst of 3 units of time. Okay, so it finish at 30. All right. So now let's look at the only one metric. So the following examples we can all look at this. This metric called waiting time. Okay, and more specifically, we'll be trying to optimize the average waiting time. Right. So remember, what is waiting time? Waiting time is the amount of time, right? Waiting time is the amount of time a process has been waiting in the ready queue. Okay, that's what we're looking at. And so this obviously we are making a lot of simplifications, right? So there's no admission delay. A process once it comes to be immediately admitted and ready to be scheduled, and there's no waiting on any IO or any event. Okay, so we consider only the waiting in the ready queue. Okay, so now let's look at the waiting time of each individual process. Okay, so for P1 the waiting time is 0 because P1 is the first one that comes to the ready queue, and once it comes, it can be immediately scheduled. Okay, it does not wait in the ready queue at all. Okay, now P2 it has a waiting time of 24. Right, that is so because P2 it comes also at time 0 and it gets scheduled at time 24. Right, and it waits for 24 units of time because that is the amount of time that it takes for P1 to complete. Right? So P2 has to wait 24 units of time, and similarly P3 has to wait 27 units of time. Okay? Starting from time 0, from here, to time 27. Okay, that's a total of 27 points of time, units of time. Right? That's the sum of runtime of P1 and P2. So now we know the waiting time of each individual process. Then we can calculate the average waiting time. Right? So we sum them up and divided by 3, which gives us 70. Okay? So 70 is the average waiting time for these 3 processes. Okay, when they come in this particular order and with this particular specific parameters of the CPU burst durations. Now, let's see what the problem could be. Okay, let's assume that these 3 processes, right, the exact three processes we are looking at here. Okay, we are still considering these 3 processes, but they come in a slightly different order. Okay, let's assume P2 comes first, and then P3 and P1. Okay, so the parameters of the 3 processes are still the same. Their CPU's burst durations are still the same, but the order is slightly different. And then let's see what happens. Okay, so according to first come first serve, right? Because now P2 is the first one that comes, so we have to schedule P2 first. Okay, and the P2 has a waiting time of 0. Okay? Now P3 is the next one to arrive, so we schedule P3 next. Okay, and P3 has to wait for 3 units of time. Okay, because that is the amount of time it takes to run P2. Right? If you come back here, P2 takes 3 units of time. Okay. And then we schedule P1 next because P1 is the last one to come in this the second example, right? And P1 has to wait for P2 and P3 to finish, and that takes 6 units of time, right? So P3 only waits for 6 units of time. Okay, so now you see that the waiting time of the 3 processes are much shorter than previous example. Okay, how do we know that? Right, if we calculate the average waiting time again, then we get only 3. Compared to the previous example, we get 17. So now do you see the problem now, right? So for the same 3 processes, okay, they all come at almost the same time, right? Just slightly different, some slight difference in order would cause the average waiting time to be very different. Okay? In the first example is 17. In the second example, 3, right? The first example is almost 5 times longer average waiting time. Okay. The second case is much better. Okay. So this problem that we see here, okay, the huge impact caused by ordering, okay, caused by the arriving order, okay, it's a so-called convoy effect. Okay, what it means is that we have a series of short process waiting for a long process to get off CPU, and that causes a convoy impact. Right, that causes the short process to wait for a really long time. Although the shell process themselves, they don't require a lot of time on the CPU. Okay, and this is bad, right? Because shell processes are forced to wait for long process. As a result, the average waiting time, considering all the processes, becomes much larger. Okay, well, a real world example, right? You can probably think of a real world example based on your own experience. Okay, for example, if you let's say you go to DMV, right? You go to DMV and there's only limit number of windows, limit the number of representatives. Okay, and you wait for your turn, right? And you don't need to spend a lot of time processing whatever you need to process. Okay, you just need a little bit of time to get what need to be done. But there's somebody ahead of you who has a lot of work to do, can taking forever. As a result, you are waiting a long time, right? So at that time, I'm certain you must be thinking, oh God, what if we can switch the order? right? And I would be, my case would be finished so fast, and that person would not even realize that I'm ahead of him or her, right? Because his or her work takes so much time, and mine takes such short amount of time, right? So if my case was processed before his or her case, right, then everybody can be happy, right? Same thing if you think this, another example would be if you go to a grocery store, right? And it just so happens you only want to buy just grab a thing and to pay for one thing. Right? Maybe you want to buy a 6-pack beer, right? That's all you want to buy, and you want to pay, and you will take probably only 1 minute, right, to check it out. But then there's someone who's in front of you with a cart full of groceries, right? So if you have to wait for that person to finish, you have to wait a long time, right? But if that person is nice, okay, and that you get ahead of him or her, right? Then he or she wouldn't really feel difference because you only take a minute, right? And he or she may take 10 minutes or 20 minutes, right? So really to the person that with a cart full of groceries, he or she wouldn't feel difference, okay, if you get scheduled ahead of him or her, okay? If he or she is so nice enough to let you do that, okay? If he or she does not like you to get ahead of him or him, then you have to wait. Okay, so those are real world examples, and in CPU scheduling we have a similar problem. Okay, and unfortunately, right? Well, if we are the designers of CPU schedulers, we can solve this problem, right? And we can if a process that has long CPU burst, okay, we can force that this non CPU burst process to wait and let the short CPU burst process is finished earlier, right? We have the control of that. While in the grocery store, when we are waiting the line, we don't have that control, unfortunately, right? But when we write a CPU scheduler, we can do that, okay? Because we know there's a problem there, okay? So now you understand, right? So first come, first serve is easy to implement, okay? It can be simply implemented by using a FIFO queue to implement the ready queue, okay? But it has this problem with convoy effect, okay? Well, the arriving order of the processes can cause a huge difference in average waiting time. Okay, so when you go back and make sure you can calculate these simple examples on your own. Okay, and at the end of this lecture, some of the problems that I ask you to do to work on, they also require such computations, simple calculations. Okay, make sure you know how to do it. Okay, although it's really simple. Okay, but don't just read it. I think you know it all. Okay, you really have to try it. Okay, because otherwise, as simple as this, when it shows up in the exam, you may just go blank. Okay, and even if you don't go blank, you don't want to spend all the time on a simple problem like this, right? Because there are other more difficult problems that you need to spend more time on. Okay, for example, if I give you a synchronizing problem to work on, so for sure it's gonna be a lot harder than a problem like this, asking you to calculate the average waiting time or the average turnaround time. Okay, so you want to finish a simple problem like this as fast as possible, so you can spend more time on a difficult problem like the synchronization problem. Okay, so I'm trying to give you some hint about how you can manage your time for a midterm, right? For exams. So in order to do that, you need to make sure that you know how to do this quickly. So you have to try it. You have to do the homework problems and try it on your own, okay, a couple of times, okay. All right, so now we know the problem with the first serve scheduling. So how do we solve the problem? We already talked about it, right? So because if we have a really long with the process with a really long CPU burst and a process with a really short CPU burst, and they come at about the same time, then we would want to schedule this process with the short CPU burst first. Okay, that will help us minimize the average waiting time. Okay, so that's the name, right? The name of this CPU scheduler is called shortest job first. Okay, the principle is we schedule the process with the shortest next CPU burst. Okay, given a bunch of processes, we schedule one with the shortest CPU burst first. After that is done, then we schedule the next one with the second shortest CPU burst. Okay, so I think let me see. Yeah. So I think I'm close to the end of the first makeup lecture. So I will just stop here. So every makeup lecture should also be 15 minutes. Okay. So I will stop here, and then I will start the next video. Okay, for our second lecture. Okay, but I upload this one first.